Welcome back. So let us examine another example. Okay, so we have a single problem here anyway. So the problem says suppose y satisfies, let's put all of the things we've done so far together. Suppose y satisfies the equation 1 minus x squared, the squared y, the x squared, minus x dy dx plus m squared y equals 0. Okay, so that's first. Show that 1 minus x squared into y sub n plus 2 minus 2n plus 1 x into y sub n plus 1 plus m squared minus n squared into y sub n equals 0. So that's the first part. Then afterwards, after we must have concluded that hence obtain the Maclaurin series, expansion, obtain the Maclaurin series expansion of G given that y of 0 equals 0 and y prime of 0. Sorry, did I write G? Where is G coming from? Obtain the Maclaurin series expansion of y, given that y of 0 is 0 and y prime of 0 is m. Right, so that's the question. So let's verify that. Suppose y satisfies the equation 1 minus x squared into d squared y dx squared minus x dy dx plus m squared y equals 0. Show that 1 minus x squared into y n plus 2 minus 2n plus 1 into x y n plus 1 plus m squared minus n squared y sub n equals 0. Okay, let's obtain Maclaurin series expansion of y. You know that y of 0 is 0 and y prime of 0 is m. Alright, so now let's get on it. This combines what we already know about, what we already learned about the, what do we call that now? The Leibniz formula for getting the nth derivative of a product of two functions. Okay, we solved questions like this when we consider the Leibniz formula. So we will do the same thing here to for this first part of the problem, for us to move from this or from this to this, or establish this from this expression, that is, knowing that this is equal to 0, then establish that this is also equal to 0. We will have to take the nth derivative, obviously, of this expression, because this is the second derivative, this is the n plus 2 derivative. So it means that for us to arrive at this, for instance, we at least need to take the nth derivative of the expression we have here. So we're going to write this out. Start with this. Take the nth derivative of this to arrive at this. This is something we've done when we did consider the Leibniz formula. So the same thing will be done here using the Leibniz formula for cases where we have a product of two functions. And after we have established that, we'll come back to answer this question and ask us to get the Maclaurin series expansion. All right, so the solution now. So we start with what we already know. Given that, given this expression, we are given 1 minus x squared multiplying the squared y, the x squared, okay, minus x multiplying the y, the x, plus m squared y equals 0. So this is what we already know about the function. Then We know that to arrive at the n plus 2 derivative, we know that we should take the nth derivative of both sides. And that means we should get the n of all of this. This is the n of 1 minus x squared into y sub 2. I mean, that is what we mean by the square, y dx squared. Then minus x into y1 or y prime if you like. Then plus m squared y is equal to the n of 0. Okay. So we'll just take the nth derivative of both sides. And from this, we're going to, we know that the derivative of a sum of two or more functions is going to be equal to the sum of their individual derivatives. So this is going to be equal to the nth derivative of 1 minus x squared multiplied by this second derivative minus the nth derivative of x multiplying the first derivative plus the nth derivative. So m square is a constant, so we can move that out of the derivative. That will be m squared multiplying the nth derivative of y. And saying the nth derivative of, I mean, this is zero. This is a constant. Whatever derivative we're getting is just zero, anyways. So we proceed from here to okay. Let's write out the ones we can simplify first. We know this is a product of two functions, so we will have to consider the Leibniz formula to simplify that. So let's leave this the way it is first. And this is minus dn of x into y1. This is the first derivative of y, the second derivative of y. But it's important to note the meaning of these symbols. Then plus this is going to be m squared. This is the nth derivative of y, so we can write that as just y sub n equal to 0. So let's leave this the way it is. It has no problem. The only things we'll have to worry about now will be this, because it's a product of two functions. Y1, that's the first derivative of y, is assumed to be some function that possibly depends on x. So that is why we'll have to use the Leibniz formula for this. And this also is a product of two functions. 1 minus x squared is a function of x. The second derivative is also a function that possibly depends on x. So we have to use the Leibniz formula for this also. So we take them one after the other to operate the Leibniz formula on them. So let's have an additional page first. So we say that to obtain um, the nth derivative of 1 minus x squared into y sub 2. So we say let u be equal to 1 minus x squared. So there's no need for this bracket. So let's leave this out. And let v be equal to y sub 2. I mean, this is what we've done previously. So the u, that will be the first derivative of u, will be derivative of 1 is 0, derivative of minus x squared, that will be minus 2x. And we're going to have the v derivative of this to be derivative of the second derivative, that will be the third derivative. And that goes sorry, so let's move on first. The squared u, before we generalize, the squared u is obviously minus 2, and the squared b will be the second derivative of the second derivative, that is the fourth derivative. And going further with this, we see that the next expression here, this one here, is going to give us the cube u, and that's the derivative of a constant, which is 0, and the cube u here, v will be the fifth derivative, which is 5. And from here going forward, all the derivatives will become 0. So the nu will be 0 for all cases where n is greater than or equal to 3. And we can also observe a general formula for this already. The pattern is obvious. That means the n of v will be equal to, you can see when it is 3, this is 5. When it is 2, this was 4. So basically when it is n, this will be y into n plus 2. So that's the general expression. So this, we are good to go. We know all the things that we need to get our Leibniz, to put into our Leibniz formula, okay, that we've obtained before. So we're going to use that quickly to just sort this derivative, okay. So we now say that, recall, okay, from Leibniz formula, Leibniz's formula, we added that the n of the product of two functions u v will be equal to, so we got the first one. Then I mean we had this general expression which I said was going to be from n equal to I'll say from k, okay, equal to 0 up to n, and it will be, okay, we used r then, so let me use r. I'm trying to remember it. So um this is n combination r, the r of u, then the n minus r of v. All right, so that was the formula we obtained earlier, which is the Leibniz's formula. So basically, we knew that the expansion would start from n combination 0, which we saw was 1. The 0 of u, that was just u, so this will be u multiplying the n v, then plus the next one will be n combination 1, so which we saw that that's what's going to give us n, and this will be n multiplying the 1 u multiplying the n minus 1 v, then plus the next one is n into n minus 1 divided by 2, and it will be the squared u, the n minus 2 v, then plus the next one, which was going to be n into n minus 1 into n minus 2 divided by 3 factorial, which was 6. Then this will be d cube u, the n minus 3b, and then it continues like that up to n, okay, whatever n was. It will continue up to n factorial n combination n, which is 1 also. So it eventually stop at n combination 1, which is 1, and that will be the 0 of v, the n of u. So that will be v multiplied by the n of u at the end of the day. So the ones for u keeps going from 0 to n, and the one for n for v keeps going from n to 0. All right, so basically this is what we need here, but we know that for our particular function now, so this is the Leibniz formula. I just wrote everything out again. But for our particular function, our u is this and our v is this, so we can just go ahead and say that. Then, therefore, it follows that the nth derivative of 1 minus x squared into y sub 2 will be equal to, we already have all the details that we need. Our u is 1 minus x squared, so this is going to be 1 minus x squared multiplied by the nth derivative of v. We've obtained that here nth derivative of v is y sub n plus 2. So this will be multiplying y sub n plus 2. And this will be plus n multiplying this, the u, that's the first derivative of u. We have that up here. That will be minus 2x. So just put in minus 2x here. So this is n multiplying minus 2x, then multiplying the n minus 1 derivative of b. So just replace n here by n minus 1. That will be multiplying y sub n plus 1. Okay. Then we'll go to the next term. That's n into n minus 1 divided by 2. And this will give us the square u. The square u, that's the derivative of this, which is just minus 2. Then multiply by the n minus 2 derivative of this, that will be just y sub n. Okay, so let's multiplying this, and this is multiplying that. And finally, the third derivative, that will be giving us 0. So this is just going to be n into n minus 1 into n minus 2 divided by 6, then multiply by the third derivative, which is 0 of u, and for this will be y sub n minus 1, and then it keeps giving us 0, so this will give us 0 eventually. So everything here will vanish to 0. So all of this will vanish to 0, so we don't have to bother about them. So basically this is going to give us, at the end of the day, it's going to give us 1 minus x squared. So we'll have this to be 1 minus x squared multiplying y sub n plus 2. Then the next one will be minus this is 2n minus 2nx into y sub n plus 1, and then this is 2 is here, so this 2 is going to cancel this 2, so I'm going to have minus left here, so this is going to be minus n into n minus 1 multiplying y sub n. All right, so basically that is what we have from this analysis here. So we know the nth derivative of expression 1 minus x squared. So let's correct this, please. This is going to be the nth derivative of 1 minus x squared multiplied by y, the second derivative of y is equal to this. So we can call this equation 1 or equation star as we call it. All right, now, so we are done with this portion. So the next thing we have to get is this one also, okay? So that will bring everything back here. So let's consider the nth derivative of xy1. So going further, we say that to obtain the nth derivative of xy1, I will say u, let u be equal to x. Let u be equal to x, so that our v is equal to y1, and it follows that the u will be equal to derivative of this, which is 1. The v will be derivative of the first derivative, that will be second derivative, and the squared u will be equal to, this will be derivative of 1. 1 is a constant, that derivative is 0, then the squared v will be equal to y3. Okay, that's the derivative of the second derivative. And from here, we know, we can already see that every other derivative going forward will be 0. So the n of what is that? The n of u will be equal to 0 for all n greater than or equal to 2. Okay, so and for this, we can conclude also that the n of v, the nth derivative of v, will just be equal to, we can observe the pattern. When is its first derivative, this was 2, so this is basically going to be y into n plus 1, right? So that's that about that. Then we now see that using the Leibniz formula, we don't want to rewrite it, using the Leibniz formula, we have it up there. So using Leibniz's formula, it will follow that the nth derivative of xy1 will be equal to, so just follow that formula. You know the first thing should be u multiplied by the nth derivative of v. So u is x, so this is going to be x multiplying the nth derivative of v is y n plus 1, so that's y n plus 1, then plus n multiplying, so we can see that up here, this is n multiplying by derivative of u, so n multiplying the u, that is n multiplying 1, then multiplying the n minus 1, n minus 1's derivative of v, that is going to be, when we replace n here by n minus 1, it is going to give us y sub n, and then plus n into n minus 1, okay, over 2, by multiplying the second derivative of this, which is 0, then multiplying the n minus 2 derivative of this, that's replacing this by n minus 2, that will be y into n minus 1. So basically we'll have that, and every other thing will become 0, so there's no need to write them out. All of this will become 0, so from here everything becomes 0, so we can just write this out clearly. This is just going to be equal to um, x into yn plus 1 plus n into y sub n. All right, so with this, we are good to go. We can just write this out and observe that this nth derivative of xy1 is equal to this expression, and we can call this equation 2. So this is equation 2. Oh, sorry, let's use our usual notation. So we call it star star. All right, so we now have the two derivatives that we need. So we can go back to substitute all of this into equation. Okay, we didn't label this. This was supposed to be our equation A by our conventions. So this is equation A. So we now substitute the expressions in the equation star and star star into equation A. So we say that moving forward now, we say substituting equations star and star star into equation A. What do we get? So let's go back to equation A. We know that the expression we got in star star and star comes first, then followed by the expression we got in star star, negative of that, then followed by plus of m squared y sub n. We equate everything to zero. So the expression we got here was what is that expression again? This is it right here. So we're just going to copy this out first. So we're going to have 1 minus x squared into y sub n plus 2. So that's the first thing here. Next is minus 2n x y n plus 1 minus 2n x y sub n plus 1. Then the next is minus n into n minus 1 yn. So minus n into n minus 1 multiplying y sub n. So we're done with the expression from equation star. Then minus, by using equation A, don't forget, minus from equation A now we have this one next, minus the second derivative that we obtained now, which is this expression here, xy. So this is going to be minus of xy sub n plus 1 plus n y sub n. So we close the brackets. Then we go back to equation A. The last term in equation A is m squared y sub n. So right, plus m squared y sub n equals 0. This will be plus m squared y sub n equals 0. So with this, we are closer to our destination. So now look at this expression. What we just need to do is to collect like terms, so to speak. So those derivatives of y, we just move those ones that are the same together. So the ones carrying y sub n plus 2, this will be 1 minus x squared multiplying y sub n plus 2. The one carrying y sub n plus 1, we have y sub n plus 1 here, we have another y sub n plus 1 here. So putting them together, this will be minus, so they both have x, okay, so but this one is 2n and this one does not have anything like that, so this is going to be minus into 2n plus 1. We move the minus outside, so it's minus of this and minus of this, then this is x into y n plus 1, okay. And the next thing is the ones carrying y sub n. So let's put them all together. We have here, if we expand this, okay, so let's say this is going to be plus, and when we expand this, this will be minus n squared plus n. I mean, this is going to be minus n squared, minus times this, then minus times minus 1, that will be plus n. Then this is another n here, but it has minus outside, so this is minus n. Then this is m squared, right? So this is plus m squared. Then y sub n. Then everything should be equal to 0. Right. So with this, we say that we now have what we are looking for: 1 minus x squared into y sub n plus 2 minus 2n plus 1 x y sub n plus 1 plus, we can see that this will cancel this, so this is m squared minus n squared plus m squared minus n squared into y sub n equals 0. And that is what we've been asked to show in the first part of the problem. So we are done with the first part of the problem. I mean, going back up, we see that that's exactly the expression we were asked to establish that was true. So I've been able to show that this was true. So we asked to show that this was true. So we've done that right now. So the next thing to do is to obtain the Maclaurin series expansion of y, given that y of 0 equals 0 and y prime of 0 equals m. So let's get back to this. So that means our y is some function of x. So that's the point here. So it's not like we're introducing any new thing. So this is one of the things we're asked to show. So we have done that part. So this is one of the answers we were looking forward to. We have it now. Now going further, we now say, so let's say that is the second part. So we now say that we are given that y of 0 equals 0 and y prime of 0 equals m. So we will work with this to obtain the Maclaurin series expansion of y. Y is some function of x. So to don't forget the Maclaurin series expansion is for when x naught is 0. So that is why we had to be provided with these functions. So we know that already. If we want to get the Maclaurin series expansion, so we recall the Maclaurin series expansion formula. Maclaurin series expansion for f of x. So for f of x was what we had before. But y is equal to f of x here, so we can just say y of x. So it makes no difference. For y is given by so to be given by y of x equals the summation from k equal to 0 to infinity of what's the expression here again? We had x to the power of k divided by k factorial, then multiplying f, that's the kth derivative of f at the point x equal to 0. So this is what we expect. Okay, this is what we need to get. So let's say new page. So this is expected for a particular function now. We don't know what the nth derivative would be. I mean, we don't know what the nth derivative will be from all of these expressions, but we can get the first few terms, okay, and just write them out first. Okay, so we know that we know the derivative at we know the value at y here. Okay, so this is going to be, sorry please, sorry, this is going to be y instead of f. So this is y, that's the kth derivative of y at x equal to 0. All right, so we know if we expand this out, it is going to give us x to the power of 0 over 0 factorial multiplying f of 0. I might, we're used to f, but it's fine. This is going to be y of 0, then plus x to the power of 1 over 1 factorial plus y prime of 0 plus x to the power of 2 over 2 factorial plus y prime prime at 0 plus x to the power of 3 over 3 factorial multiplied by y prime prime at 0 plus x to the power of 4 over 4 factorial multiplied by y 4, okay, at 0, and that continues forever. Okay, so the expansion gives us this. So we need to have these terms. We already know y at 0. We already know y prime also at 0. So the next thing we need to bother about is y prime prime at 0 and possibly the third derivative and the fourth derivative and so on at 0. But looking at the relations we were given, look at what we were given. We were told that we were told here that In the question, we're told that the second derivative, 1 minus x squared multiplying the second derivative minus x multiplying the first derivative, then plus m squared y equals 0. So we're going to use this here. We already know y when x is equal to 0. We already know y prime, which is the y dx when x is equal to 0. We need to find first the square y dx squared when x is 0. So we're going to use this expression. So let's quickly get that out of the way. So we produce this relation. So we produce this relation. We say that to find y prime prime at 0, okay, we recall that we've been given 1 minus x squared multiplying the squared y the x squared. This is part of the information given in the question, which we have used to verify another information provided as well. Minus x multiplying the y dx plus m squared y equals 0. So then at x equal to 0, we're going to have 1 minus 0, which is 1. So this is the square y dx square. Let's just write it as y prime prime, okay, of 0 minus x, that is 0, multiplying the y dx. So they gave us already that the y dx is m at 0, then plus m squared multiplied by y. They told us that y is 0 at 0, so this is going to be equal to 0. So from here we see that y prime prime is equal to 0. So we take note of that. We're going to use it here, so we'll put it back here when we're ready. Another thing is this y prime prime prime, so the third derivative. And to do this, to get this third derivative and subsequent derivatives also, we have another relation which is supplied and which we have also verified. We have it here. This is supplied in the question. We have verified it as part of the solutions to this problem. So with this tells us that if we have the nth derivative, we can get the n plus 1th derivative and the n plus 2 derivative. So if we have the first derivative already, we know that now we can get the second derivative. We can connect it to the second derivative here and use it to get the third derivative. That means when we set n equal to 1, we can use this formula to obtain the third derivative. And when we have the third derivative, we can set n equal to 2, use this formula again to get the fourth derivative. So we can get all subsequent derivatives from the point where we have the first and second derivative. That's why this information has been supplied like that. So let us make use of this now to obtain the third derivative. To obtain the third derivative, y prime prime at 0, we make use of this relation. We recall that 1 minus x squared into y sub n plus 2 minus 2n plus 1 into x into y sub n plus 1 plus m squared minus n squared y sub n equals 0. So from this, we now see that for y3, we can set n equal to 1. So when we set n equal to 1 here, and we are interested in the value at x equal to 0, don't forget. So we set x equal to 0 as well. We're going to have this to be y into 3. So this will be at x equal to 0, this will be 1 minus 0, which is 1. Then this will be y, because we are evaluating this for when n equal to 1. This will be y sub 1 plus 2, which is 3. Then this will be the value at 0 that we're evaluating. So whatever the value of 0 of this is, then minus 2n. So that will be 2 times 1 plus 1, that is 3 into x is 0, multiplied by y sub n plus 1, that is 1 plus 1, y sub 2 at 0, whatever that is, then plus m squared minus n squared, okay, into y sub n, that will be y sub 1. So this will be y sub 1 at 0. So all of this should be equal to 0. So obviously this is 0 since we've multiplied this by 0. So what we have left with is And we have been told that y1 at 0, that's y prime at 0, is equal to m. We're given that in the question. So from here, we can see that y sub 3, or y prime prime prime, y prime 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 at 0 is equal to, when we move this to the other side, this will be m into m squared, or say n squared minus m squared if you like. So that will be n squared minus m squared. I mean, by the time we move this to the other side, we become negative. So, and they told us already that this derivative at 0 is 1. So we take note of that and we are good to go. And if we want to obtain the fourth derivative at 0 also, we come here and set n equal to 2. When we set n equal to 2, we make use of the second derivative and the third derivative to give us the fourth derivative. The same manner, when we want to get the fifth derivative, we do the same thing, and so on and so forth. So we can play around with that as an exercise. You can get the fourth derivative at 0. You can also get the Okay, you can also get the fifth derivative at 0. Okay, just use this formula in terms. Use it for when n equal to 2. You substitute here. This will be second derivative, third derivative, fourth derivative. So you already know third derivative, you already know second derivative. You make the fourth derivative the subject at x equal to 0. It will give you your result. And to get the y sub 5 at 0, you make n equal to 3. At n equal to 3, this will be third derivative, fourth derivative, fifth derivative. You would already have known, by that time, you will already have known the fourth and third derivative. So you can use them right there. So that is that about that. We can just proceed and by inserting all of the things we already know into this expression. So we get our Maclaurin series for y of x. So having obtained all of this, we now say that therefore, finally, our y of x, Maclaurin series expansion for y of x. So let's get back to the terms one after the other. We know the first term is x to the power 0, which is 1. 0 factorial is 1. So this is 1 multiplied by y of 0. We know y of 0 to be 0. So this is just going to be 1 multiplying 0 plus the second term. The second term is x to the power of 1 divided by 1 factorial. That is x over 1. This is x multiplying y prime at 0. We've been told that y prime at 0 is m. Okay, that's given in the question. Y prime at 0 is m. So we have that already. So we're going to put that right here. Y prime at 0 is m. So this is going to give us y prime at 0 is m. So this is x over 1 multiplied by y prime at 0, which is m. Then plus the next one is x squared over 2. So we already know the pattern. So the next one will be x squared over 2 multiplied by y prime prime at 0. So this is x squared over, sorry, that's x squared over 2 factorial multiplied by y prime prime at 0. We obtained y prime prime at 0 already. We found it to be 0. Okay, so that's the expression here. Let's indicate that this is at 0, please. Y prime prime at 0 is equal to 0. So we can use that, okay, right here. So this is going to be x squared over 2 factorial multiplied by 0. Then plus the next one, that will be x cubed over 3 factorial multiplied by y prime 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 prime. So that's the third derivative. We have seen that it is m into n squared minus m squared n squared. So this is going to be m into n squared minus m squared. So put that there, then plus like that and like that. When you've obtained this, you can insert that as well and continue like that. But it's fine. We already have the first few terms, unless a specific term is specified. Once we have the first few terms, so it's up to 3 or 4 or 5. Fine. So this is going to be 0. So this one is 0. So forget about that. So what we have here is xm. So we can write it as mx. Then this is 0 also. So you can forget about it. So what we have left will be m. So that will be plus m into n squared minus m squared. Okay, into x raised to power 3 over 3 factorial, which is 6 plus the terms will proceed like that. So we get the fourth derivative, we can use it to get the term corresponding to s to power 4. You can get the term corresponding to s to power 5. You can get the term corresponding to s to power 6, and so on and so forth. But this is the pattern as follows, and that will be our results for the Maclaurin series expansion of Y. All right. This should not carry n, please. There's an error in what we've done here. We already said we should set n to 1. We already said n should be set to 1. Okay, so this was supposed to be 1. Sorry, please. Sorry. This is 1 squared, which is 1. By the time we get here, n squared is 1, please. We already set n equal to 1. So this is not meant to carry n any longer. It should just carry m. That's our constant there. Okay. So at the end of the day, this should be 1, just 1 right here. So this is 1, and this should be 1 minus m squared. Yeah, so that is that. So subsequent ones also, I mean, just like we substituted for the others here, we substituted for n equal to 1 here, so we ought to have substituted for n equal to 1 here as well. So it didn't have to carry n. There was no need for that. All right, so that is that about that. That's the end of this lesson. Thank you for watching.